All right, let's look at the Maclaurin series of sine of x and also cosine of x. All right, so let's start with sine of x. All right, so we want to, let's see, I'm going to call the sine of x f of x. All right, so this is sine of x. All right, so let's keep on taking a derivative. So first derivative is cosine of x. All right, then the second derivative is negative sine of x. And the third derivative is negative cosine of x. And the fourth derivative is positive sine of x. So you can see that they kind of went back to the original function, right? So it's going to repeat itself. So this is going to, it's a cycle of 4. So it's going to keep on doing the same thing. All right, then since it's a Maclaurin series, I'm going to just plug in 0, x equals 0. All right, so sine of 0 is 0. And f prime of 0, cosine of 0 is actually positive 1. And second derivative at 0 would be a negative sine of 0 is still 0, right? Then you have the third derivative at x is 0 is a negative cosine of 0 is negative 1. And the fourth derivative, of course, is the same as the original function, so it's going to be 0. Right? So this pattern just keeps on going. All right. So it looks like every let's see, odd function. Sorry, not odd function. Odd derivative is going to, the first derivative is 1, and third derivative is actually negative 1. So and all the even derivative, so no derivative, second derivative, fourth derivative is going to be equal to 0. So we can see that the Taylor series, so it's going to n goes from 0 to 1, infinity. All right. So we only get the odd terms. All right. So we can indicate that by doing x to the 2n plus 1. Right. Then, of course, you have an n factorial, but you only have odd terms, so you have 2n plus 1 factorial, right? And then odd term alternate between positive 1 and negative 1, so we have to put the negative 1 to the n, right? So this is the Maclaurin series of sine of x. Right, so it looks like an alternating series, and it makes sense that since the sine is an odd function, it only uses the odd power terms. All right, let's look at the variation of this, and we can find the cosine of the Maclaurin series for cosine by using a derivative. Right, so for example, you know that sine of x is cosine of x can be actually it can be obtained by taking a derivative of sine of x, right? Because derivative sine of x is exactly equal to cosine of x. So what we can do is we can just take the derivative of the Maclaurin series, which is summation n goes from 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial, right? Then we just take the derivative of this guy, right? So I'm going to change that to square bracket there, right? Right. So one of the benefit of power series is that since each term is a power function, so you can just use the power rule to take the derivative and term by term. So this is going to be, right, so you have a summation, still the same summation there, right? Negative 1 to the nth power is just a number, so derivative, constant multiple, so it doesn't change, right? And also 2n plus 1 factorial on the bottom doesn't change, so I'm going to write the 2n plus 1 factorial, right? But we have to apply the power rule to find the derivative of x to the 2n plus 1. So what you do is you put the 2n plus 1 in front of x, then subtract 1 from the power, so you have a 2n, right? Then if you notice that 2n plus 1 factorial is equivalent to 2n plus 1 times 2n factorial, right? So what we can do is you can cancel out the 2n plus 1 and 2n plus 1 on the bottom, and you find the Maclaurin series for cosine. So it's a summation and goes from 0 to infinity, and negative 1 to the n, right? You have x to the 2n over 2n factorial, right? Again, this kind of makes sense because cosine is an even function, and you can see that its Maclaurin series only uses even power terms, right? So those are the Maclaurin series for sine of x and the cosine of x, right? That's it. I hope that this was clear.